Today I'm going to start chapter 2. So now we're getting ourselves into calc. In the previous couple of lectures it was review of pre-calc, namely algebra and some trig. So we're going to get to limits and derivatives. As I always tell my students, there are 4 legs of calculus, 4 legs. The first leg is limits, which is the most important one. The second one is continuity, the third one is derivative, and the fourth one is integration. These are the 4 legs of calculus: limits, continuity, differentiability or the derivative, and then integration or integrals. There wouldn't be any calculus without knowing limits. You will see everything we talk about goes back to limits. So it's extremely important to understand limits, and that's what we're about to start in 2.2. 2.1 there's barely anything. I kind of embedded it in 2.2, so that's why I'm skipping 2.1. The limit of a function. So I'm going to start limits using an example. So if f of x equals x squared minus 4 over x minus 2, I want to use a table of values to find the limit of f of x as x is close to 2. Because if you look at this, if you try to do f of 2, it's going to be 0 over 0. We don't know from algebra, we don't know what that is. So what happens if I approach 2 from the left? So if you look at the number line, 2 is right here. What happens if I plug in 1.5, 1.9, and 1.99, and then got 2.1, 2.01, and so on? I want to just understand what. So I'm going to plug in some values, and I'm going to use my calculator to do the work. 1.9999 to 2.001, 2.01, and then 2.1. And I'm going to do f of x. So if you go to your calculators and key in the function, let's delete what's in there, y equals x squared minus 4 in parentheses divided by x minus 2 in parentheses. And see, it says I want to key in my own values. Since I want to key in my own values, then I want to go to table and table set and make sure my independent is on ask, which is. Then go to table, and then I'm going to delete all these values. So I'm going to plug in 1.9, 1.99, 1.999, and so on to get the y value. So I did all this, and here's my answers. So I got 3.9, 3.99, 3.999, 3.9999, and it's undefined here. We don't know what that is. This would be 4.001, 4.01, and then 4.1. You can see as x approaches 2, as we're approaching 2 from this side, as x approaches 2 from the left, so on the number line from the left, that means x is less than 2. Y is approaching what? So I'm using right arrow for approach. Y is approaching 4. So let me rewrite this. So as x approaches 2, and we put a little minus here, that means it's coming closer to 2 from the left side, which means 1.9, 1.99, and so on, less than 2. Y approaches 4, and as x approaches 2 from the right, 2.1, 2.01, and so on, y is also approaching 4. This means the limit as x approaches 2 is 4. When we say limit, the limit value is the y value. The limit value is the y value, which is in this case 4, and x is that value. Okay, so to write this, as x approaches 2 from the left, y goes to 4, we use limit. We put x approaches 2 from the left underneath it of f of x, which is x squared minus 4 over x minus 2 is 4. It's like plugging the number in, but you can see plugging it the 2 in doesn't work. So let me rewrite this here. X approaches 2 from the left of x squared minus 4 over x minus 2 is 4. And the limit x approaches 2 from the right of x squared minus 4 over x minus 2 is 4. If these two limits exist and they're equal, then we can say the common limit as x approaches 2 of x squared minus 4 over x minus 2 exists and it equals 4. And we're going to write down a general definition for this. Suppose f is defined when x is close to a, except possibly at a. It may be defined at a, but it doesn't have to. A in our example was 2. Then the limit as x approaches a, which is 2 in our example, f of x equals L, which was a 4 in our example, exists if the left limit exists as x approaches a, f of x equals L, and the right limit exists. When we say exists, that means you have a value for it, and this value has to be the same as that value. Okay. So at your house, I want you to do, I'm not going to do that for you, I want you to do this. ln of x minus ln of 2 over x minus 2. Use your calculator and do a t-table just like I did, and your answer should be 0.5. Okay, so check that out. So this is kind of homework for you, extra homework. Now, can we say the limit of a function always exists? No, we cannot say it always exists. We're going to talk about the common types of behavior where the limit does not exist. So, common types of behavior associated with non-existence of limit as x goes to a, f of x. First, the limit will not exist if f of x approaches a different number as x approaches a to the left than as x approaches a to the right. An example about that, if you have f of x equals the piecewise defined function f1 if x is 0 or more, and -1 if x is less than 0. If you graph it, there's open circle at 0 from the negative side, there's closed circle here because of greater or equal and less than 0. So as you're approaching 0, because you want to know the limit as x approaches 0, so as you are approaching 0 from the left of f of x, you can see this is 0, but you're coming this way. So like -1, -1.5, -0.2, 0.1. What's the y value equal to? -1. And as x approaches 0 from the right, coming this way, the y value is 1. You can see, although both limits exist, they are not what? They are not the same. F of x approaches different limit, different number when x approaches a from the left than when it approaches a from the left. We say the limit does not exist in this case. Okay, the limit does not exist. Number 2, the limit will not exist if f of x goes to infinity, whether it's plus or minus infinity, as x goes to a plus or a minus, whether you're approaching a from the right or from the left. F of x equals 1 over x. You can see if you graph 1 over x, as x approaches 0 from the right or from the left, either y goes to infinity or y goes to negative infinity. So one of them is enough. As x approaches 0 from the left, it goes to negative infinity. So we say the limit as x goes to 0 does not exist. Does not exist. And the third one is very uncommon, but it happens. F of x oscillates between two fixed values as x approaches a. For example, the limit as x goes to 0 cosine 1 over x, it does not exist, since if you look at the graph, of cosine 1 over x, cosine 1 over x, you can see as x gets close to 0, well, this is not a good graph. Let's go to window and go to zoom and do z trig. See, near 0, it actually should oscillate more than this. You can't say whether it's 1 or negative 1. It doesn't really, it's not clear. It keeps oscillating. So since the graph oscillates, oh, sorry, let me zoom out. Since the graph oscillates between negative 1 and 1 as x approaches 0. Okay, let's look at number 6, page 92. In number 6, page 92, you need to be looking at the graph and then answer the questions. And you should have the graph right here. For the function h whose graph is given, state the value of each quantity if it exists. If it doesn't, explain why. So the first question is, I'll just do a few of them and then you'll finish that at home. The limit as x approaches negative 3 from the left of h of x. Limit as x goes to negative 3 from the left. So if you look at negative 3 right here, from the left, your y value is 1, 2, 3, 4. It's 4. And then part B, the limit as x goes to negative 3 from the right. Same thing, negative 3 from the right is also 4. Since they both exist and they're equal, part C, the limit as x goes to negative 3 of h of x equals 4. Okay? Here's the work. Okay, and then you can answer the rest of the questions. It's not hard. You need to be looking at the graph. So I can give you the answers though. It's for D, h of negative 3 is undefined. For E, the limit as x goes to 0 from the left of h of x is 1. Limit for F as x goes to 0 from the right, h of x is negative 1. That means the limit as x goes to 0 does not exist. Why not? Because these two values are not the same. The left limit is not the same as the right limit. Okay, and so on. You can, the rest is simple once you know this. Okay. Now infinite limits. So here's an example about infinite limits, and then we'll talk about the definition. So if you let f of x equals x over x minus 2, then obviously f is undefined at 2. Okay, f at 2 is undefined. That's from algebra, because you get 2 over 0. Now we're going to use a t-table and see what happens when we approach 2, just like the previous example. Okay, so if I approach 2 from the left and from the right, well, if you put that in your grapher just like I did, you will get negative 19, negative 199, negative, so you can see what's going on with the y values. So you can see as x, the limit as x approaches 2 from the left of x minus 2, it looks like it's going to negative infinity. It's going to negative infinity. And over here, the limit as x goes to 2 from the right of x over x minus 2, it's going to positive infinity. So we say the limit does not exist. Remember, this is one of the cases where the limit does not exist. If one of them is infinity, then we say the limit does not exist. Okay, what's the definition? Now we just saw an example. So the definition of infinite limits. So let f be a function defined in a neighborhood of a except possibly at a. So it has to be defined around a, around that number. Then the limit as x approaches a, f of x equals infinity, means the values of f of x are increasing, and if it was negative infinity it would be decreasing, increasing without bound, as x approaches a. And say, like I said, if this was negative infinity, it would be decreasing without bound. Okay, so let's look at number 30, page 93. The limit as x goes to 5 from the left, x plus 1 over x minus 5. Okay, so basically if you plug the 5 in, 5 or 5 minus 4.999, you're getting 6 or 6 minus over 0 or 0 minus, which is, it's less than 5, minus 5, it's 0 minus. So any number divided by 0 is infinity. Positive over negative is going to be negative infinity, okay? So if you have a positive over 0 minus is negative infinity. If you have a negative over 0 minus, two negatives make a positive, and then if you have a positive over 0 plus, two pluses is plus. If you have a positive number over 0 minus, it's negative. So just positive over negative, or positive over positive, negative over negative, or negative over positive. Okay. 34. What's the limit as x goes to 0 from the right of ln of sine x? Well, if you plug 0 in there, sine of 0 is 0, whether it's 0 plus or 0 minus. Ln of 0 is negative infinity. So this is ln of 0, which is negative infinity. Why ln of 0 is negative infinity? Because if you look at the graph of ln, as you're approaching, you cannot approach 0 from the left. So you have approaching 0 from the right. What's the y value going to? Negative infinity. Okay. And why is this 0 plus? Because you're doing sine of 0 plus, which is 0 plus. If you, again, that's knowing the graph of sine. As you're approaching 0 from this side, you're getting 0 plus. You're getting 0 above the x-axis. Okay, 34, we did that. Another example. Here's an example. the limit as x approaches 2 from the left, x squared minus 2x over x squared minus 4x plus 4. So if you plug the 2 in there, you get 0. 4 minus 8 plus 4 is also 0. What we can do though, we can factor x, and then you can factor this x minus 2, x minus 2. We can cancel that out and then plug it in. So you get 2 over 0, which is infinity. Plus or minus infinity doesn't matter. This is 2 minus, and this is 0 minus, because 2 minus, and then 2 minus minus 2 is 0, less than 0, so it's positive infinity. Okay. Finally, we're going to do vertical asymptotes from this section. Vertical asymptotes. The shortcut is VA. So the line x equals a is a vertical asymptote to the graph of f if the limit as x goes to a plus f of x is plus or minus infinity, or the limit as x goes to a minus f of x is. So if whether it's left limit or right limit gives you infinity, then you say x equal a is a vertical asymptote. Now, for example, if you have, say, f of x equals 1 over x. If you look at 1 over x, if you know the graph, you can see as x approaches 0 plus or 0 minus, you're getting infinity. Limit as x goes to 0 plus f of x is infinity, or 0 minus would be next. So x equals 0, which is the y-axis, is a vertical asymptote. Okay? Now, if you have rational functions, it's easy to find vertical asymptotes. If it's non-rational, then you're going to do the definition. For rational functions, f of x equals g of x over h of x. To find the vertical asymptotes, you reduce first if it's possible. You divide by any common factors, then set the denominator equals 0 to find all vertical asymptotes. If it's non-rational, then you're going to use the definition. Okay, so if it's non-rational, like this one example, find vertical asymptotes of number 1. This has nothing to do with rational functions, it's a log function. So to find the vertical asymptote, we want to use the definition. We know log functions, this is a log function moved 3 units to the left. So basically, it's ln of x moved 3 units to the left. So basically you have a graph like this if you graph it. And obviously from the graph x equal -3 is a vertical asymptote. So if you see as x approaches -3 from the right of ln of x plus 3, you're going to get ln of 0, which is negative infinity. 0 plus, which is negative infinity. You can see that. So x equals -3 is a vertical asymptote. Okay? So you kind of need to know a few things to do that. And how do we find the vertical asymptote for g of x, which equals x plus 3 over x squared minus 9? The limit as x approaches 3, -3 of g of x. If you plug it in, you get what? 0 over 0, but it's a rational function, so we can reduce it first. So if you reduce it, what do you get? G of x equals x plus 3 over x plus 3, x minus 3, which is 1 over x minus 3. If you set the bottom equals 0, So x equals 3 is a vertical asymptote. And if you graph it, you will see that the graph breaks down at x equals 3. For f of x equals negative 4x over x squared plus 4, this has no vertical asymptotes. Why not? Because the denominator can never be 0 for real numbers, okay? X squared plus 4 is never 0. And for tangent x, remember tangent is what? Sine over cosine. So this will have vertical asymptotes when the bottom is 0, because anything over 0 is going to give me infinity. So cosine x equals 0, where x is going to be an odd multiple of pi, pi over 2, odd multiple of pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so on, plus or minus, of course. Okay, and that's all I wanted to do in terms of